Thought I'd lead off the video here showing you what your homework is going to be and what to expect the next couple of days. So this will be a 2-day project. We'll work on this Monday and Tuesday. By Wednesday we'll be reviewing sections 2.1 to 2.3, and by Thursday we'll be taking a quiz over sections 2.1 to 2.3. So it gives you kind of a timeline of where we're going to be. There are two basic objectives in this lesson. We got to be able to know how to divide polynomials by using long division and synthetic division. And the second thing is to use the remainder and factor theorems. The first one we're going to try to do is we're going to try to teach you how to do division of long division of polynomials, and then we're going to show you how synthetic division can be used as well. It's a little bit faster process, a little cleaner and easier process. So they initiate this conversation by saying, look at this function f of x. It's a third-degree polynomial, so we know the shape. It's an S-shaped graph. It's going to be going from low to high, and I've actually graphed that here for you in red. So this is the picture that goes along with the function rule. What they say, if you know that f of x has a 0 at 3, and I can tell graphically that 3 is a 0 this function, which means if we were to plug in the 3 in for the x's in each of these locations and evaluate, the output, the function f at x, or f at 3, would be 0. And that's what this order pair 3, 0 represents. It represents the 0 of the function. A lot of times we'll call these roots of the function. 3 will be a root if it's a solution, which it is. So that's the one we're really focused on right now. So then if x equals 3 is a 0 of the function, that meant that x minus 3 had to be a factor of the function f of x. And because f of x was a third-degree polynomial, and we pulled out a linear term, which is a first-degree polynomial, and which means we divided this by a first degree, then the third degree divided by a first degree should give you a second degree. And that's where they say, you know there exists a second degree polynomial, q of x, such that a first degree polynomial times a second degree polynomial end up giving your third degree polynomial that we started with. So what we're saying is we can divide this by x minus 3, and we can break it down into a smaller polynomial. And that's what we're going to be working on. And we're going to do this with long division. So we're going to use an algorithm similar to that of division with integers. I'm just going to show you this process, and then you can go further into the textbook if you want to look at some more examples there. It says factor each polynomial completely by using the given factor of long division. So what they do is they first give us a polynomial that we're supposed to divide into. They're going to tell you to divide by x plus 6. Now what I'm showing you again is the graph of this. The graph and the factors in the original polynomial go hand in hand. So our original polynomial x cubed is the blue graph. We want to see if x plus 6 is a factor. Well, if x plus 6 is a factor, then x equals a negative 6 should be a 0 of the function, and you can see that our graph is crossing at a negative 6, if I could just hit the point. We could also see graphically that it looks as though there should be a negative 2 as a factor, but if as a 0. But if negative 2 is a 0, then we can relate that back to a factor, which means eventually we should be able to figure out there's got to be an x plus 2 as a factor. And then reasoning similarly, if we go over here, it looks like it's crossing at a positive 1. So that is a 0 of the function. So if it's a 0 of the function, then there must be a factor of x minus 1. So we're going to look at breaking this whole thing down into 3 factors. But we're going to do it in a reverse process. We're going to do it using our long division. So anyhow, let's get started with the long division. We set it up just like we would set up long division for integers. So 7x squared plus 4x minus 12. We want to divide this polynomial by the linear polynomial, which is x plus 6. So this is how I think of this. What do I multiply x by to get x cubed? In order to get an x to become an x cubed, I multiply by an x squared. So now I take x times x squared, which is x cubed. I take this x squared times 6, which is plus 6x squared. Okay, now typically after you get done multiplying in long division, you will end up subtracting. So what I end up doing is using a little rhyme here. I draw the line, change the signs, and rather than having to remember to subtract every time, if I draw the line, change the signs, I'm going to add. And now I'm positive x cubed minus x cubed is 0. A 7x squared minus 6x squared is a positive x squared. Now with all long division, after you get done subtracting, or in this case we added the opposite, you bring down your next term, so plus 4x. Now, what I got to reason again is, what do I multiply this x by to get an x squared? Well, if I take an x times another x, I'm going to go plus x, then I can get an x squared. So this x times that x is x squared. This x times 6 is plus 6x. Okay, so we just got done multiplying. So we're going to draw the line and change the sign so that instead of having to subtract, we're always going to add. So when we add, an x squared and a negative x squared is 0x squared. And 4x minus 6x is a negative 2x. After you get done adding or subtracting, however you want to think of it, you bring down your next number. In this case, it's a negative 12. Now I'm back to the same reasoning. What do I multiply this x by to get a negative 2x? So in order to do that, I'd have to multiply it by a negative 2. A negative 2 times an x is a negative 2x. A negative 2 times a positive 6 is a negative 12. I want to draw the line, change the signs, and add. And when I add, I end up with the remainder of 0. So this x plus 6 divides evenly into our original polynomial function, x cubed plus 7x squared plus 4x plus 12. Okay, so now the next thing that we're going to do is we're going to take those factors, and we're going to see if they'll factor even a little bit more. I can just get this to scroll up. So I got an x plus 6. If I take this times x squared plus x minus 2, I should end up with the original polynomial I started with, which is x cubed plus 7x squared plus 4x minus 12. In our directions, we're supposed to completely factor this as much as we can. So I know the x plus 6 is already a linear term and it's factored as much as we can. But a quadratic could be factored again. So what we're going to try to do is factor this into two more linears. So the factors of x squared are x and x. The signs have to be different, plus and minus. The factors of 2 that we need are 2 and 1. I want to have a positive 2 and negative 1. So this polynomial here factors into 3 linear factors. And these 3 linear factors now, if we think of solving this, we want to force the output to be 0. And when the output is 0, if x is a negative 6, a negative 2, or a positive 1, we now have the zeros of the function, which are the x-intercepts of the graph. If we come back up to our original graph, or use this instead, you can see those are exactly the places where it's crossing. At a negative 6, at a positive or negative 2, and at a positive 1. And those are the ones that we identified here. Now, I went a little beyond what they ask you to do. All they're asking you to do is use the long division to find the factors. You didn't have to relate that back to the solutions or the zeros, but I did anyway because we're going to link it eventually. Okay, so now we're going to try and practice this one more time. We start off with a cubic function. So again, a cubic function should be S-shaped. So there's our S-shaped graph. It goes from low to high. What we want to do is we want to take the 6x cubed minus 2x squared minus 16x minus 8, and we want to divide it by using long division of 2x minus 4. Now I have the graph there, the 2x minus 4. If 2x minus 4 is a factor, that means it would have to equal 0, which means 2x would have to equal a negative 4, which means x would have to equal a negative 2. I'm going to look at the graph, and does it cross exactly at a negative 2? And that is, no, it's not, which probably means it's not going to go in there evenly. We'll have a remainder left over here. So we'll go through. All of this is concentrating on your long division. So what do I multiply 2x by to get a 6x cubed? That's the first line of thinking. So I got to take a 2 times a 3 to get a 6, and I got to take an x times an x squared in order to get 6x cubed. So we multiply 3x squared times a 2x, which is 6x cubed. I take the 3x squared times negative 4, which is a negative 12x squared. Every time after you get done multiplying, draw the line, change the signs, because instead of subtracting, we're going to add the opposite. So this was a positive 6x cubed, so it's going to be negative 6x cubed, and it was a negative 12x squared, so we're going to make it plus 12x squared. So draw the line, change the signs, we're going to add, those will eliminate each other, we'll end up with 10x squared. And after you get done with subtracting, you always drop down your next number. In this case, it's the next monomial term, which is 16x. Okay, now we're back to the same strategy. What do I multiply 2x by to get a 10x squared? and that is by 5x. So plus 5x. 5x times 2x is 10x squared. 5x times a negative 4 is a negative 20x. Draw the line. Now we're going to change the signs. Rather than subtracting, we're always going to add the opposite. Reduces the number of pairs that we make. So these will reduce. Negative 16x plus 20x is 4x. Now once we're done subtracting, or in this case adding, drop down your next term, negative 8. Okay, so what do we multiply? What do we multiply a 2x times to get a 4x? So 2x times a 4x, we multiply it times 2. So we're going to put plus 2. And 2 times 2x is 4x. And then 2 times a negative 4 is a negative 8, which gives me a remainder of 0. So now all of a sudden it's dawning on me that I had an error back up in here. When I solve this, this should be 2x. And if I add 4, it becomes plus 4. And then if I divide by 2, it becomes a plus 2. And was that positive 2 a 0? That meant it had to go in there evenly. So what the long division is telling me is that it did go in there evenly, that if 2x minus 4 is a factor, then x equals a positive 2 must be a 0 this. So we're supposed to continue with this factorization, because what we've found right now is that if we take 2x minus 4 and divide it into 6x cubed minus 2x squared minus 16x minus 8, we now have 2x minus 4 as a factor. The other factor is a 3x squared plus 5x plus 2. If we multiply these two together, it should give us exactly what we started with again. 6x cubed minus 2x squared minus 16x minus 8. The only problem is that this one is not completely factored, and I would argue that this one isn't completely factored. They gave us one that wasn't. So I'm going to factor out a 2 out of this. If I factor out a 2, we're going to get an x minus a 2. This triangle will factor into two binomials. The factors of 3x squared have to be 3x and x. We do know that the signs have to be positive, plus and plus, because this is positive and the inside term is positive. The factors of 2 have to be 2 and 1, so I'm going to put the 2 in this location, the 1 in this location, so the FOIL process will end up giving us outside, inside is a 5x, because you got a 3x and a 2x add up to a 5x. So I'm going to get rid of those marks. So really what we have it as is that this original polynomial that we had has 3 linear factors, 1, 2, 3, and it has a constant. So this is what we're asked to do, use long division to factor the polynomial completely. Put a little plug back into this graph over here that we had at the top. What I know is from this equation that x should cross at 2, because 2 is a 0 of the function. If we solve this one, we have to take the opposite of adding 2, so subtract 2, then divide by 3, so it's a negative 2/3. Our graph should cross negative 2/3, and the graph should cross again at a negative 1, and that's if I set this equal to 0. So again, see if 2, negative 2/3, and a negative 1 are where your graph crosses the x-axis. And it's easy to see the 2, it's easy to see the 1. What's a little bit more difficult is where this is exactly, but it gives us at least a little bit of glimpse of where that might be, and that is at our negative 2/3, negative 6.67, or however you want to think of it. So there's an example of long division. It's very similar to your process that you've used for long division of numbers. Multiply, and then subtract, and then bring down your next number. So